Hello everyone, welcome back to this channel. We are studying class 11 physics. In that chapter number 6, work, energy and power. So in the previous video we started with the initial topics of scalar product and how to find out or calculate scalar product. We have also gone through the concept of work and related units and dimensions. So today we are going to start with part 2 of this chapter series video, and the topic is work done by variable force. Right, now the question arises, what is the meaning of the word variable and why it is attached with the word force? So the meaning of variable force is the force which is not constant throughout the process. Earlier you might have gone through the questions like, if force is this much newton and the displacement is this much meter, the work done is having some value. But in that case, if you have concentrated that force was only 10 newton or whatever newton, that was constant throughout the displacement. But what if a work is going on and the force keeps on changing? So how shall you find out the work done, because it is not same throughout the process? So let us suppose a variable force F is acting on a body along the fixed direction, say x-axis. Remember, variable force F. Okay, so let us plot a graph of force versus displacement, and then we'll try to find out the work done, and we will assume that initial position was xi and final position was xf, and this displacement from initial position to final position is done under the force F. So here is the graph. You see, on the y-axis we have fx and it has change in its values. You see, the initially the force was this much, then gradually it keeps on increasing and decreasing. That shows that the force is variable, changing. Initial position is xi and final position is xf. So what is the displacement from here to here, right? So now what will be our work done? The area under the curve will give us the work done. Remember, the shaded portion is the area, and that area if you find, you will get the total work done. So now the next question arises, that if the area under the curve will give us the work done, how to calculate area if the shape is irregular? Because till now we have gone through the formulas of various areas of different shapes, right? Triangle, half base into height, right? Square, accordingly we have a formula, side into side, rectangle, L into B. But those all shapes were regular shapes, but now it is curve. So how to find out the area? So now we will apply a trick. You see in the figure what we have done, we have divided the total displacement. If you see from xi to xf, we have divided this whole area into small rectangles. Okay, so let us suppose there are n number of rectangles. So if you focus on any one rectangle, what is the area of rectangle? What is the area of rectangle? Area of rectangle is L into B. Over here, what is the length? Length is the force acting. And what is the breadth? Breadth is the small displacement which is being done. So if we focus on this rectangle, what will be the area? It will be force into displacement, F into delta x. What is delta x? It is displacement, very small displacement, right? So now if you are able to know the area of this rectangle, can you know the area of all these small rectangles, right? And if we know the area of all these small rectangle, and if you add them, you will find the area of the curve, area of the portion below the curve, right? So we will have to add all the areas of the small rectangles lying under the curve. So what do? We do the summation, right? So I have kept this summation symbol sigma from xi to xf, initial to final, f into delta x. Now, taking limit delta x tends to 0, the summation will give us a finite value and which will be equal to the overall, the total work done. So now if we take the limitation delta x tends to 0, removing the summation, we will now have to use the integration symbol, right? So w equals to limit delta x tends to 0, summation of f delta x from xi to xf is equal to integration of xi to xf into f dx. So this will be the total work done. Now let us talk about energy. We have seen the concept of work. Now let us start with energy. What is energy? Energy of the body is defined as its capacity or ability to do work. You can also write capability. Now the energy of the body is measured by the amount of work the body can perform. Therefore, like work, energy is also a scalar quantity. Point to be noticed. The dimensional formula of energy will also be same as that of work. The energy is measured in same units as the work. So which kind of quantity? Scalar. Dimensional formula same as that of work. Energy same as that of work. Now there are different forms of energy in this universe. We have come across many kinds of energy, many forms of energy: mechanical, sound, heat, light energy, chemical energy, atomic energy, nuclear energy, electric energy, magnetic and solar energy, etc. Right? Now, important thing to note in physics when we talk about mechanics, the important energy form is mechanical energy. The energy produced by mechanical means is called mechanical energy. Or in standard 9 we have also learned about that what is mechanical energy? It is the sum of two different forms of energy which are kinetic energy and potential energy, right? Why we are talking about mechanical energy? Because we are studying mechanics, and for mechanics kinetic and potential is very important as far as mechanics is concerned, as far as this chapter is concerned. So important words I have highlighted, you see: capacity or the ability to do work, scalar quantity, dimensional formula is same units, right? Different forms, and what is mechanical energy. So these are main ideas related to energy. Now let us start with kinetic energy. What is kinetic energy? It is the energy possessed by the body by virtue of its motion. So this is called kinetic energy. A moving object can do work. It has the capability to do work. The amount of work that a moving object can do before it comes to rest is exactly equal to its kinetic energy, right? For example, there are many real life examples also in which you can see the role of kinetic energy is very important. For example, a moving hammer can drive a nail into the wood, fast moving stone can break a glass window, bullet fired from a gun can hit the target, kinetic energy of air is used to run windmill, and kinetic energy of water is used in dam to produce electricity. So kinetic energy or the energy of moving object is very important. If an object of mass m is traveling with velocity v, kinetic energy of that body is said to be half mv square. Now this concept you already have studied in 9th standard, so it is just a kind of revision. So by the formula, how we can define kinetic energy? The kinetic energy of a body is equal to half the product of the mass of the body and the square of its velocity. So this is all about kinetic energy. Now let us try to obtain a relationship between kinetic energy and momentum. See, kinetic energy 1 half mv square, momentum is m into v as we have learnt. Let us start with the original formula of kinetic energy, that is half mv square. Now you may understand that momentum, as it contains m and v, they both are present in the equation of kinetic energy. So what shall we do now? Let us multiply and divide both the multiply and divide the right hand side, sorry, with m. So here in numerator we will have an m extra, also in the denominator we will have another m. So you see clearly, in the numerator we have m into m, that will convert into m square. Rest everything will remain the same. In numerator again, if it is m square v square, we can combine them into a single bracket and will write mv whole square. Now here in this step we can put p instead of mv. So whole mv whole square will become p square upon 2m. So this is the relation between kinetic energy and momentum of a body. K equals to p square by 2m. Accordingly, you can interchange for potential for momentum. The next topic is work energy theorem. It is very important as per exam purpose. Also, it is a theorem. It is a kind of relation which combines the kinetic energy and the concept of work done. Okay, so let us see now. Suppose force Fx act on a body of mass m. The work done under the influence of this force will be W equals to integration initial to final Fx dx. Now we all know that what is force? Force is mass into acceleration. So we have just replaced Fx with m into a. Now again, what is acceleration? Acceleration is change in velocity per unit time. So what we did, we just replaced acceleration with dv by dt. Now if you take this dt from the denominator to the denominator of dx, how shall the equation look like? It will look like this: m into dx by dt into dv. Now what is dx? It is change in position. What is dt? Change in time. So change in position with time is nothing but velocity. So I have taken the m, which is constant, in forward, and now instead of dx by dt we have v, and dv will be repeated. See, step by step this process is very easy, but you have to focus. Right, from force we obtain ma, mass into acceleration. From acceleration, dv by dt. Take the dt towards dx, so it will be dx by dt, and just replace dx by dt with v. Now let us suppose that initial velocity is v1, final velocity is v2. So instead of initial and final, we will write v1 and v2. So let us see how this equation looks like. M integration v1 to v2 v dv. This we are finding nothing but work done. Now, the result of integration by utilizing proper formula will be v dv is v square upon 2, right? Right now the power over here is plus 1. So what will be the integration? It will be v raised to the power plus 1 upon 1 plus 1, right? N plus 1 upon n plus 1. So v square by 2 will be the answer. So lower limit and higher limit will be written after the bracket. So v2 is written upward and v1 is written downward. This is the limit. Okay, upper limit, lower limit. So now the next step is very important. One time we will keep the upper limit instead of v, minus another time we will keep lower limit instead of v. So now it will look like this: m, first we will put v2, so it will be v2 square by 2, minus in between, now v1 square by 2, right? And if you see carefully, we have m outside, which is common for both of them. So we will one by one multiply this m to each term. So here it will be half mv2 square by 2 minus half mv1 square. Now half mv square, we have known that it is nothing but kinetic energy. So v2 square will be final kinetic energy, v1 square will be initial kinetic energy. So ultimately it is W equals to final kinetic energy minus initial kinetic energy, and this is nothing but the work energy theorem. So what does work energy theorem say? Work energy theorem says that work done is equal to change in kinetic energy of any object, right? Suppose the object was having some kind of initial velocity, and if the work is done, then the object will attain different amount of value of velocity. Its velocity will change, accordingly its kinetic energy will change, and this difference in kinetic energy is nothing but the work done. So this is work energy theorem. So that's it for this video. All the topics that we have gone through in this video is important. So kindly make the notes properly and watch the video carefully. Thank you.